there, I'm Sergeant Mullins. Say I have a problem for you. I have a high-frequency transmitter and receiver in this room and a radiating antenna at the top of this tower. Can you tell me how to transfer energy from the room to the antenna and radiate the energy into space? Well, some of you say with a transmission line, and you're right. But we still have a small problem. It is not a straight line from the room to the antenna. Then, too, the antenna is rotating. Well, can you imagine what would happen if we connected a piece of waveguide from the transmitter to the antenna? You're quite right. We would have a waveguide pretzel. So let's start at the receiver transmitter unit and see what we'll need to get the energy to the antenna. Here is a mock-up of the particular section of the system we are interested in. Now, because of the position of the RT unit, the waveguide is coming out the side in a horizontal position. The antenna is located above the RT unit, so we have to change direction and go in a vertical direction. Well, we can do this just like a plumber would do it if he were putting plumbing in a house. We can use an elbow or a 90-degree bend. Of course, this bend must be inserted into the waveguide and connections made on either end of it. So we will use choke joints to make the connections. Now we come to this area of the system where the stationary waveguide must be connected to a rotating section on the antenna platform. This connection is made with a rotating joint which is enclosed in this housing. Just before we get to the end of our system, we have to change the polarization of the energy to properly feed the antenna. So we put a 90-degree twist in the waveguide. Now, at the end of the line, we have to get the energy out of the waveguide and send it out into space without losing too much power. And to do this, we use a feed horn. And finally, if we had to work on the system while it was in operation and we didn't want to radiate any energy, we could connect a dummy load, such as this, to the antenna or the transmitter to absorb the energy rather than radiate it. Now, upon graduation from this school, you will not be expected to be able to design a system such as this, but you may be required to work on one similar to it. So it's important that you at least be familiar with the physical construction and the electrical operation of the different components of the system. And during this lesson, we will discuss the choke joint, the rotating joint, the feed horn, and the dummy load. We will also identify E and H bends in a waveguide and see what happens when the waveguide is improperly bent. Well, our problems have been laid out for us, so let's solve them one at a time by starting back down here at the RT unit with the bend in the waveguide. Now, we will discuss two types of bends, the gradual E bend and the gradual H bend. Here's a picture of the E bend. Well, can you imagine why it is called an E bend? Well, as you know, lines of force in the E field within a waveguide travel from B wall to B wall. So when the B wall is bent in this manner, the E field will receive maximum distortion. Now, since the E field is distorted more than the H field, we call this bend the gradual 90-degree E bend. You will notice here is a picture of the E field lines of force within this section of the E bend. For explanation purposes, we are not showing the complete number of lines of force within the section. Actually, there will be many more lines of force within both the bended section and these sections. Now, using this diagram, let's consider how the E field is affected when the B wall is bent. You will notice that here and here, the E lines of force are normal. But right here, where they round the corner, They are stretched farther apart or distorted. Now, we mentioned that this was a gradual bend. By gradual, we mean the electrical distance from the beginning of the bend to the end of the bend must be at least 2 complete wavelengths. This minimizes any reflections and losses. Remember that any time a waveguide is bent, the radius of the bend must be at least 2 complete wavelengths. Now here is a section of waveguide with the B-wall bent. You'll notice that the B-wall is the wide wall. Notice also that the bend is gradual. Remember that the radius of the bend must be at least 2 complete wavelengths to minimize reflections and prevent losses. Another type of bend is the H-bend. The H-field lines of force travel between the A-walls of a waveguide. So when the A-wall is bent, the H-field will receive maximum distortion. And for this reason, we call this bend the gradual 90-degree H-bend. Now here's a picture of the H-field lines of force within this section of the H-bend. Again, for purposes of explanation, we're not showing the complete number of H-field lines of force. Let's consider what happens to the H-field lines of force when the A-wall is bent. Again, here and here, the field is normal. But right here at the bend, you'll notice that the H-field lines of force are stretched out or distorted. Again, the radius of the bend must be greater than 2 complete full wavelengths to minimize losses due to reflections. However, the bends must be made gradually. If they are too sharp, they will cause reflections and losses. A bend may be greater or less than 90 degrees, depending upon the requirements of the individual system. Also, if any dents in the walls of the waveguide, these will also cause reflections and losses. So when you get out into the field and start to handle a waveguide, be careful with it and try not to dent or bend it in any way. Here is a section of waveguide with the A-wall bent. You'll notice that the A-wall is this narrow wall. Again, the bend must be made gradual. The radius of the bend must be at least 2 complete full wavelengths to minimize reflections and prevent losses. Well, let's now complete item number 1C in the TVI guide. This item reads, an E or H bend in a waveguide may be more or less than 90 degrees, but the radius of the bend must be at least 2 wavelengths for each 90 degrees. You fill in the numeral 2 in the blank space. Now, this bend which we have inserted into the system must be connected both physically and electrically to the rest of the system. And we said we use a choke joint to make the connections. This choke joint gets its name from a component you are already familiar with, the RF choke. You'll recall that the RF choke is used in electronic circuits to choke off the RF energy and keep it in the part of the circuit where it belongs. The choke joint accomplishes the same thing for the waveguide. It prevents the energy from escaping from the waveguide where the physical connections are made. Now, since every system is different in its physical and electrical requirements, there are several different sections and components which go into the making of an entire system. The choke joint is used to connect these sections. Also, if a piece of section, or rather if a particular section of the waveguide got damaged and had to be removed, we would simply disconnect the section at the choke joints and replace it rather than having to replace the entire system. Let's see how the choke joint connects two sections of waveguide physically and electrically. You'll notice here we're showing a cross-section of the choke joint. In this representation, the gaps between the two sections has been overemphasized for explanation. Actually, the two sections are screwed together to hold them securely. Sometimes a thin gasket material is inserted between them to prevent the seepage of air so that the line can be pressurized. The energy will travel through the gasket material, enabling us to establish standing waves in the slots. Even with the sections pressed this tightly together, there's still enough gap between the two sections to allow the energy to escape. So we must close the gap electrically to prevent losses. And here's how it's done. You'll notice that one side of the choke joint is just a flat flange, this side here. And the other side is slotted. It is these slots that are important. Notice that the parallel slot here is 1/4 wavelength deep with respect to the main waveguide. And the perpendicular slot here is 1/4 wavelength long with respect to the center wall of the main waveguide. Now remember that we need an electrical short at the points where the walls of the two sections connect. You will notice that the parallel slot is shorted at this end. Now, what will this short reflect 1/4 wavelength away? An open. It will reflect an open at the top of the perpendicular slot. And what will this open in turn reflect? 1/4 wavelength away, or here, at the wall of the waveguide. A short. So here where the two sections meet, we have a point of low impedance. And the one waveguide wall is effectively shorted to the wall of the other section, electrically, even though the walls may or may not touch physically. The physical construction looks like this. You'll notice that here is the flat flange on this section. And here is the slotted section. This has been cut away to show the slot. Here is the parallel slot, which is 1/4 wavelength deep. Here is the perpendicular slot, which is 1/4 wavelength from the wall of the waveguide. Now here we have a cutaway of an actual choke joint. You will notice that here is the perpendicular slot. And here are the parallel slots. Well, so far we have turned the corner and are headed in a vertical direction. Now we come to the point where we must make a transition from the stationary waveguide to the rotating waveguide on the antenna platform. This housing surrounds the rotating choke joint to hold it steady. If we were to take a peek inside of the housing, we would see something like this. Does it look familiar? Well, it should, because its construction is very similar to that of the fixed choke joint. The only difference is that in order for one section to rotate, this section here, and the other to remain stationary without disturbing the electrical characteristics in the waveguide, the waveguides themselves must be circular. Naturally, the transition from rectangular to circular waveguide must be made at the ends of both sections. Now, electrically, this rotating joint operates the same as the fixed choke joint. You will notice that here is the perpendicular slot, and here is the parallel slot. Both are still 1/4 wavelength long, and the standing waves in the slots gives us the proper electrical characteristics to keep the two sections connected electrically, yet they may or may not touch physically. Now, this purpose of the rotating joint is stated under item 3 of your TVI guide. Let's complete this item. The rotating joint enables us to connect a rotating section of the waveguide to a stationary section electrically, yet keep them separated physically. Electrically goes in the first blank, physically in the second blank. You will also note that the electrical characteristics of the rotating joint are identical to those of the fixed choke joint. Now, because of the constant rotation of the antenna, there will be movement and vibrations present in this part of the system. Prolonged vibration will have an adverse effect on anything that is held rigid. So to overcome the effects of vibration, we use sections of flexible waveguide in the system. Here is a section of flexible waveguide. You will notice that it can be bent or twisted in any desired direction. Let's consider what this section of flexible waveguide is constructed of. You will notice that it consists of a spiral-wound ribbon of brass. The assembly is like a spiral spring in that it can be bent or twisted into any desired shape. You will notice that the outside of the section is covered with rubber. This gives the section flexibility and at the same time makes it both airtight and watertight. RF energy travels through this flexible waveguide just exactly the same way as it does through the rigid waveguide. Well, at this point in our system, we come to a few more bends to physically situate the waveguide properly with respect to the antenna reflector. However, for the particular system we are discussing, the energy is not correctly polarized to give us the desired radiation pattern. We can change the polarization of the waveguide by putting a 90-degree twist in it. Here is a picture of the 90-degree twist. You'll notice that the twists must be made gradual. This is to minimize reflections and losses. The electrical length from the beginning, or rather from the start to the finish of the twist, must be at least 2 complete wavelengths. Now here's a section with, or rather a section of waveguide with a 90-degree twist. Notice that the twist is made gradual. Remember that the electrical distance from the start to the finish of the twist must be at least 2 complete full wavelengths. Now we are at the point where the RF energy is to leave the waveguide and be sent into free space. I'm sure you must realize that the characteristic impedance of the waveguide is low as compared to the impedance of space, which is several hundred ohms. In order to get the maximum transfer of power from the waveguide to space, we must match the impedance, and our impedance matching device is called a feed horn. A feed horn is actually a tapered section of waveguide, and it matches the characteristic impedance of the waveguide to the impedance of free space by making the impedance change gradual rather than abrupt. For instance, here's how the E-lines are affected. As the E-lines travel down the feed horn, they get longer and longer as the impedance increases. Now, by making the impedance change gradual, we have minimized reflections and losses. Of course, the angle of taper of the feed horn will depend upon the frequency of operation of the system and upon the antenna's physical requirements. Now here is an actual feed horn. You will notice it's nothing more than a tapered section of waveguide. On this end is where the choke joint connects to the waveguide. And again, this is, this is the tapered section that gradually changes the impedance from that of the waveguide to that of free space. Now, for our final objective, let's go way back down to the RT unit. Let's assume that for some reason we wanted to work on the RT unit under normal operating conditions. But for one reason or another, we did not want the antenna to radiate any energy. How can we operate the set without sending out any energy? Well, we could put some device in place of the waveguide that will absorb rather than dissipate, or rather than send the energy to the antenna. The device we use to do this is called the dummy load. In order for the dummy load to absorb and dissipate all of the energy we feed into it, it must be highly resistive. And they are commonly constructed by making the walls of the waveguide from a power-absorbing material such as powdered graphite and a cement binder as a power-absorbing material. This section of the dummy load is inserted right into the waveguide to match the impedance of the waveguide to that of the dummy load. Now, because the dummy load is so highly resistive, all of the energy entering it will be dissipated in the form of heat. These wafer sections you see here are the cooling fins to give us more cooling surface area. Even with all these cooling fins, the dummy load can still become very warm when the set is operating. The actual dummy load looks like this. Here is the part that's used to match the impedance of the waveguide to that of the dummy load. And here are the cooling fins. Now, the first point we discussed in this lesson was the bends in the waveguide. We learned that when the B wall was bent, we called it an E bend, because the E fields received maximum distortion. Remember that when the B wall is bent, we call this the gradual 90-degree E bend, because the E field receives maximum distortion. When the A wall was bent, we called it an H bend. In this case, the H field lines of force will receive maximum distortion. Remember that the radius of the bend must be at least 2 complete wavelengths to minimize reflections and losses. We also saw that it was possible to twist a waveguide to change the polarity of the energy. But here too, the twist must cover at least 2 complete wavelengths to minimize reflections. Now, in such cases as rotating antennas or any place where motion or vibration are factors, flexible sections of waveguide are used to absorb the vibrations. Flexible waveguide is used where freedom of motion is essential. Now, all of the sections of the waveguide must be connected together to make a complete system, and we cannot afford to lose any energy at these connections. So we use a choke joint to make the connections. The choke joint, through the use of standing waves in the slots, produce points of low impedance or electrical shorts at the wall of the waveguide. This type of section is electrical but not necessarily physical, as in the case of the rotating joint. In the rotating joint, where we cannot have a physical connection, the 2 sections are physically separated and are rigidly supported so that one section is free to rotate and the other is stationary. This joint makes an electrical connection between the 2 sections of the waveguide. Now, to match the impedance of the waveguide to the impedance of free space, we use a tapered section of waveguide known as the feed horn. By making the impedance change gradual rather than abrupt, we can obtain minimum loss in the transfer of energy from the waveguide to space. Finally, we discussed a device called the dummy load. Remember that this is a highly resistive component that can be inserted into the waveguide to absorb and dissipate RF energy rather than send it out into space. A dummy load is used anytime it's necessary to operate the set without radiating any energy. This completes our study of waveguide plumbing. Take a few close looks at your TBI guide because all of the material we have discussed is covered in it. So long.